Alright, today I'm gonna talk about something related to the multi-agent system, which I'm pretty sure you guys are all very familiar with. So today I'm talking about the SWE agent, software engineering agents. But before I talk about these slides, I want to do like a quick poll, like quick question, like maybe how many of you have developed a multi-agent system before? Like, nice. I see a lot of raise of hands. Okay, for those of you who have raised your hand, I have a further question for you. Is actually that's also a question one of the executives at Salesforce asked me, which I was stuck. I was stuck. I have actually like zero, like no response to him. Like I was like but still I don't really have a concrete answer to his question, and I'm pretty sure he's not satisfied with my answer in the end. But today, I hope after this presentation we all can have an answer to that. And that question is there any specific problem or use case in the world that a single agent cannot do, but multiple agents can help? Okay, that's I think the core value of multiple agents, right? Like why we need multiple agents, why multiple agents right now is not as popular as a single agent framework, and what we can do to make multi agents great. Okay. All right. So today we're gonna talk about SWE agent, and as a startup, I'm pretty sure you guys are all very familiar with the benchmark of SWE-bench. I think a lot of startups are, creating better models, better agent frameworks to get on the top of the leaderboard. And after they get in the top of the leaderboard, they can raise fundings. Basically, that's how the value of this benchmark, like why people are, getting like allocate a lot of people to work on this specific benchmark. Recently, I know there's a startup called Cosine Genie, and they use I think they fine-tune GPT-4o on some data sets they collected using similar data sets on the SWE-bench, and they can achieve a pretty high result rate on the SWE-bench. And after that, they get fundings from Salesforce, they get fundings from OpenAI. They even met Sam Altman last week. I mean, this benchmark is the value of the benchmark is basically for the startups is if they have very high scores on this benchmark, it'll be pretty easy for them to get more funding. Okay. So, but what this benchmark is about, like what's the tasks that are going to be solved by this benchmark, and how motivations can help. Okay. So the input is usually like a GitHub issue, right? Like the task is to fix a bug or add a new feature to your GitHub repo, a very large GitHub repo like sklearn, right? And you will be given a real-world issue scrape from the PR from the GitHub repo, right? You have the issue description. In this case, end user find out there's a data leakage in this gradient boosting tree algorithm, and some people will join this discussion talking about what are the possible features to add and what is considered as a success, right? What software engineers will do, right? Propose some new features, describe what they expect of them, and ask some engineers to implement it. Okay, that's input, and given this input and some SWE agent with language models, it'll generate a PR, basically multiple code changes in multiple files. We call it diff hunts, and then there will be some ground truth testing written in the benchmark to test whether these PRs can pass those unit tests or not. If all the unit tests they pass the unit test, then you earn 1 score on the benchmark. Okay, and that's what this benchmark is about. The input is an issue, output is a PR, and they will be evaluated by the ground truth golden unit tests. Cool. Right, there is like a more detailed example, right? Model input, instructions, what the issue looks like, right? And Also the benchmark provides a gold patch, but your generated patch can be totally different from the gold patch as long as it passes the ground truth test. And here's some stats about this Sweetbench benchmark. Right, in the most comprehensive benchmark, Sweetbench original, it has around 300 issues from 12 open source repos. You can see django, Secular, Seaborn, PyLink, PyTest, all those are and matplotlib. All these are very popular and well maintained open source repos, and it'll contain a ground truth unit test to evaluate the model generation. Also, they also have another small set of this Sweetbench, because running one pass over those 3,000 issues using some agents will cost more than $1,000. Basically, evaluating once will cost more than $1,000. That's why they also have this small set of the benchmark called Sweetbench Lite, which only has like 300 issues. And most companies, most startups are competing on this benchmark. Also, OpenAI just added a new one 2 weeks ago called Sweetbench Verified. It's also like 500 issues from this Sweetbench original, and OpenAI guys claim that they did some manual evaluation of those issues to validate whether those issues can be solved or not. Basically, doing some human evaluation of the benchmark, selecting some ones that are guaranteed to be correct. And yeah, that's it. That's the 3 benchmarks on the Sweetbench. Sweetbench original, or Sweetbench full, Sweetbench Lite, and Sweetbench verified. And if you develop an agent, you can test it on all of the 3 benchmarks. All the interfaces are the same. It's just one will cost more dollars and the other one costs less. And right, and if you look at the benchmarks, the agents on the leaderboard, there are a lot of startups posting their solutions there, and some of them disclose some technical details, but most of them don't. For those who have disclosed their technical details, we find out their agentic loop mainly contains these 3 stages. Okay, stage number 1, given an issue, right? Given a repo map, or you need to index the whole code base, right? To do RAG. So after you do that, do all those pre-processing, the first thing is to given the instruction, given the code issue or the GitHub issue, you will need to find out which files you want to change, what code span, like which code blocks you want to change. It's this fault localization, pretty similar to how navigation is in robotics. You need to first use the RAG, use the index to search for relevant files, right? Then you look at files one by one to see, okay, should I edit this code block or not, right? This kind of stuff. And after you retrieve all those relevant contexts, relevant files, the next stage is code editing. You break down you create a plan from the GitHub issue, right? And for each code block, you'll have edit instruction. And you use the best LM you can have, Cloud 3.5, GPT or Xlam, to edit those code blocks, direct edit to the code blocks. And finally, for some of those really advanced agents, right, they'll have this retrying step to close the loop. Basically, they'll also generate some tests. Well, we cannot get access to the ground truth test. That's unfair. But we can, use the LM, given the instructions, given the GitHub issue, can generate some tests, and use those tests to test whether your code changes passes your generated test or not. If not, just retry. Yeah, and that's usually what those frameworks look like. I really don't see any very huge differences between those agents that disclose the details, but I'm not sure about those closed source ones. I think the real differences is how in each stage the different agents will have different implementations, and also they'll probably have different prompts. Prompts really matter, and also like for a cosine genie, they also have their own model. I think that's also the reason why they can claim they're top one on the Swift. Okay. Any questions so far before I jump into our solution? Okay, and then here's like a more investigation into the current results on Swift. These are open source solutions, and the cells with color means this issue can be solved by that agent. These white ones means they're not able to be solved. You can imagine this is basically a summarization of the current SOTA agents on the Swift. You'll see that even though they are using very similar frameworks, very similar design, they have completely different passive base success, right, on different issues. That is one thing we discovered from the results, right? Like even though they're having almost the same phases, but because of different implementation, different prompts, they actually succeed at different GitHub issues. And the second thing we find out is they're super unstable. Basically, maybe you run it once, this issue will be solved. You run it for a second time, it won't. And this is also very unstable. We call it very diverse, but basically it's the same thing. So we have find out two diversity for those three agents here. One is different agents, although they follow the same design architecture, are very diverse in terms of their solved patches. Second is internal diversity, like different runs will generate different patches, and those patches solve different GitHub issues. So naturally we'll be thinking about how multi-agents can help, right, in these situations. Like how multiple agents can combine the expertise of those agents of different trials to achieve a better success rate. And that is what we are doing here. Our ensemble framework, our multi-agent frameworks, this one here, you can actually doing pretty good on the matplotlib, I think, right? It kind of combines the expertise of different agents and also achieves a significant improvement in other repos as well. Here's like a more high-level summary. Like here's what different open source agents perform. Here is what we perform, and this is Oracle performances. And all right, let's talk about how we are able to do this. So, given a GitHub issue first, right? We have different kinds of agents that all of them are able to at least take the issue, okay, and identify different locations of fault. And we're going to have a fault localization committee to judge which one is the best, right? After you select the best fault locations from here, right? Then you'll give it to a second patch of agents, which will be used to modify those patches. Finally, you'll have a patch review committee to judge which code changes is the best. It's a pretty simple design, but it's first follow the kind of leverage the shared workflow of those multi-agents. Of those three agents framework. Right? Usually, first stage is fault localization. The second stage is code editing, and at each stage, we're able to use the multi-agents. We're able to spend more budget on the inference time, right, to get better performances, and we're also leveraging the expertise of different agents at different stages across different trials. But the question is, how do we design this committee then? Right. Then here's how we design this committee. Okay. Well, first retrieve the relevant context, right, for each stage. which usually will be 10 lines before and after the code change. And we'll get the full file before the code patch, full file after the code patch, and for those candidate patches, it will also be it will also be given as inputs to the committee. And what the committee does is first it will critique the solutions, give them the give an issue explanation, explain why you want to change it, and explain the patch, explain if there's any conflict. Finally, it'll give a score, and from those scores, you will select the top K, and if the committee is happy with the solution, they'll submit the solution. Otherwise, it'll go back to the group. Yeah. That's how this SWIC committee or DI committee is working. And you'll be surprised how this simple design can boost the overall performances. So this is the cosine genie I introduced just now, and it has a 50% result rate. If we simply just combine the top two agents, we're able to get 5% improvement. If we ensemble those red agents, right, the second tier agents, we're able to get like 6% improvement. And if we just integrate those open source solutions, that's even huge. It's around like 7% improvement. Basically, for both good agent models or bad agent models, this kind of a simple multi-agent design, ensemble design, all helps. I know there could be a lot of different complex stuff we can do to make the multi-agents even better, but even just by simply ensemble those agents directly, right, just re-ranking those solutions, you are able to get a huge improvement. And that's where I believe multi-agents can really shine. For the reason why we want to aim for a multi-agent world, not a single agent world, is not because multiple agents can really solve complex tasks that single agent cannot. It is actually because there are already so many agents there. Even today, there are so many SWIC agents there, and there needs to be a orchestration layer or multi-agent world, whatever you call it, to better organize, manage those agents. And it's not because there's actually some use cases or problems that a single agent cannot do, but multiple agents can. It's because in reality, there are already thousands of agents out there, and there needs to be a multi-agent orchestration layer to help manage them. Otherwise, those agents will be alone. A second question I can answer to that executive's question is my answer so far is why is because actually when we are implementing those agents, our initial idea is not to pursue for this multi-agent solution, is to integrate the tools from different agents, integrate together into one powerful agent. That's our initial design. But actually find out integrating is hard. Refactoring is very hard. It takes time. And this is my intern's project, and he's only here for like 2 months. There's no time for him to refactor all these agents into one agent. But if we're not aiming for a single agent solution, or just aim for a multi-agent solution, then integration will be much easier. You don't need to change any code in those agents at all. You just need to add an orchestration layer at the top, and it can use the expertise of different agents that are highly simplified the software engineering development. Saves you guys tons of efforts. That's also like the second point I want to talk about today, like why we want multi-agent system, not a single agent. Yeah. All right, here's some more results. Those curves are hard to understand, but I'll explain one by one. So this union oracle is the basically oracle performance is if this ensembling multi-agent thing works like a gun, that's the performances you'll achieve, right? Like you basically see that like if you have more agents, then you see this Oracle performances will be higher, but eventually it'll hit a bottleneck. And this is our performances. You see, it's not perfect, but in the initial period, it's still improving. And what this intersect at K means, it means basically if this basically like an intersection between different solutions. For example, like if an issue can be resolved by all agents across all rounds, then we'll say, okay, this is a success. This is a measurement of the stability of the agents. Basically, you don't really want an agent to succeed just for once. You want it to succeed for all the rounds. You'll see that for all these 3 open source agents that we are able to run, everyone can run. You see that it's pretty unstable, right? Like if you add more rounds, usually like it'll be very unstable. But with our solution, you can see that it's actually not. Actually boost the resolved performances, also boost the stability of the solutions. That's the beauty of multi-agents. All right, I think that's it for my slides. And if you like this work, you can go to this website, look at the code, and give a star and sign our paper. Yeah.